Okay, I'm going to be talking about molecular clouds and chemistry beyond the Milky Way eventually, but I want to introduce myself first as an undergraduate of Alex's, and I did 2 papers with him starting my junior year. I did a junior tutorial paper with him on the chemistry of silicon in interstellar clouds. And then I did my senior thesis on associative detachment and H2 excitation in... Okay, it's not loud enough, sorry. In the interstellar medium. I think it's really remarkable that there's a session on undergraduate research. That's really unusual. So I'm very honored to be here to speak. And I was trying to think back, and it's been a while, it's been 30 years, so it's quite a while since I've been an undergraduate. And so I was trying to think of anecdotes and things and realized it really has been quite a while, but he's still influencing me. Although my first thought on flying into Logan about the 30 years was that I think the statute of limitations has passed on my parking tickets. I don't know if anyone else here who may have been a grad student had a stack of parking tickets this high, like I did. You know, you get a parking ticket, you shove it in the glove compartment. And that was the Cambridge Police Department in the days before computers. It was great. The second thought was Tommy Gold. And he came to mind because I showed up for my weekly session with Alex, and I'm waiting. And Tommy Gold had dropped in to see him, and he got kicked out of the office for me. So here I am, a junior, right? And I know that I know dimly, because I know a little bit of science, that this guy is important, and he's getting kicked out for me. But Valerie was very firm. She came in, she was very polite, but firm. She said, "Alex, Gina's here." So Tommy Gold got kicked out. Okay, we all knew this, but this was just a real demonstration that students were the most important thing. And finally, I'd just like to say he's influenced my thinking about working with undergraduates myself. I do work with undergraduates at UCLA. And I realize now it's very difficult to work with them simply because they don't know a lot. So, for example, I'm working now with a physics student, and he was top of the class in my statistical mechanics class. Bright guy. Comes into my office and doesn't know what Unix is. So you have to teach them Unix. They don't know how to program a computer. They don't know numerical methods. They're still learning math. They're just learning quantum mechanics, and you have to do research with them. It's really not easy. So it's a very giving interaction on the side of the professor. So I'm very grateful. And now I know what the other side is like. So the fact that I got 2 papers out of my undergraduate research was much more due to Alex than it was due to me. At any rate, what I'm going to talk about today is sort of a combination of what I ended up doing. I went on to, does this involve me? I went on to Berkeley to work with Jack Welch, and Jack worked with towns to discover the first polyatomic molecules in space, including ammonia and water. And so I was working with him on the first millimeter interferometer. I'm interested in galaxies, and so I've been doing this almost since the beginning of millimeter interferometry. And most recent work is imaging chemistry. So the chemistry takes me back to what I was doing with Alex. So he has influenced sort of my choice of scientific research even 30 years later. In terms of working with chemistry and galaxies, I'd like to point out that 1 arcsecond resolution, which is very good in the millimeter, is equal to 20 parsecs, even in the closest galaxies. And for single dish work, and there have been many spectroscopic studies with single dishes, including the Aerom 30 meter, you're talking about kiloparsec size scales in galaxies, basically, very large fraction of the galaxy. So I think interferometry is a great way to isolate regions and get a better idea of the chemistry, but you're still talking about chemistry on the size scales of giant molecular clouds. There's been a lot of work, for example, Avina has done a lot of work on the structure of protoplanetary disks and how much you can learn from the variation in chemistry across those disks. That is a factor of 1,000 higher resolution than we're talking about here. So there are differences in the chemistry. It's just really remarkable that we're talking about on such large size scales. And the particular instruments that were used for this research were Owens Valley and BIMA, which have now combined together to form CARMA. And of course, this is going to be a subject of ALMA research too, when it comes along. This particular work was with my graduate student, my former graduate student, David Meyer. And I wanted to put his picture up here because there are 3 David Meyers, unfortunately, in astronomy. There's one at JPL who spells his name the same way. There's another one at Northwestern. This is the one who's just moved to New Mexico Tech. Here's a spectrum of NGC 5253, and this was made with the IRAM 30 meter, first unbiased line survey in a galaxy. And you can see there's a lot of molecules in galaxies. There have been many detected. And ALMA will improve the situation. So you can actually do chemistry. It's not just all CO. The 2 galaxies I'm going to discuss today are IC 342 and MAFI 2. These are gas-rich nearby galaxies, and so the line emission is bright. IC 342, which is on the left, is a large face-on, late-type spiral galaxy. MAFI 2 on the right is a barred galaxy. It might be interacting slightly, but they're both about the same distance away, and the boxes show the region that I'm going to be showing you in the maps. So the primary beam, that's the field of view of the millimeter interferometers, is small. It only covers the very nucleus. So this is right around the dynamical center of these galaxies. General overview of IC 342, I showed you optical images. This is a near-infrared image on the upper left. Do I have a pointer? No. All right. Out on this side, the far upper left, that's a near-infrared image, and you can see sort of a slight bar to this galaxy. It looks pretty axisymmetric, but there's a slight bar, which bars tend to funnel gas into the center of a galaxy, and so that's probably why it's gas-rich. If you look at the color picture at the top, that's a combination of H1 and CO. So the centers of galaxies, basically the optical portion of a galaxy tends to be in the form of CO, the gas. The outer parts of a galaxy tend to be H1. It's believed that this is a pressure effect, but it's a large-scale effect that's seen in many galaxies. And the bottom image is an optical image, and this is what the CO looks like in the very center. Thank you. So the CO is the contour here, and you can just sort of see that it's a bar-like structure in the center, and in the very center there is some star formation. Okay, here's a schematic of what's going on. This bar is caused because you have gas orbiting around in the center. So there is gas here also, but it tends to pile up along the spiral arms, and there's streaming. So it will come in, it will stream and flow radially in this portion of the arm, and then it will move radially outward here and then stream in again. So you have these orbits, and the orbits are kind of discontinuous here. If you look at the rotation curves and the kinematics, you can see a real gradient across this arm. So there's probably a shock there. We can't really resolve it, but across here is something like 50 to 60 kilometers per second across maybe 50 parsecs. So the likelihood of shocks is very great, and we know that there's also streaming here. So these molecular clouds are being stressed. Now, in the grand scheme of things, if this were the outer part of a galaxy, you would see star formation. You might see molecular clouds come in, get compressed, form stars. We do see a little bit, but I think more often than not, the star formation does not occur in these arms because of the shear. So these clouds are not collapsing. Instead, as they flow into the nucleus, they end up in this inner Lindblad ring. They orbit around, and there's star formation where the arms meet the ring. You have the drift inward of the gas, the gradual drift inward, and at some point it's got to form stars because as this gas slowly drifts in about 1 kilometer per second, a few percent of its rotation speed due to dissipation and angular momentum transfer in the arms, you do get a drift inwards, and at some point you have to use up that gas. Something's got to happen to it. And in fact, there is a nuclear cluster here that's about 60, 70 million years old. So there's star formation going on. This is our theory as to what's going on. It may be going on in the galactic center also. That may be the origin of the large clusters in the galactic center, although it's controversial. So that's the picture of the center of a spiral galaxy. Here's what it looks like if you look at various molecules. We set out to do this originally with a single dish, but we ended up doing it with Owens Valley, which is a very slow process. It took us several years to gather all this data. But we have HNC, HC3N, N2H+, C2H, C34S, methanol, HNCO. And the remarkable thing is that even though our resolution is the size of a GMC, we see remarkable chemical differences. These molecular clouds have very different characteristic chemistries, which, if you think about photodissociation regions, a lot of the action happens within only a few AV. So magnitudes, visual magnitudes of 1 to 2 is where a lot of the chemical action happens. You get molecules forming and things, a lot of the chemistry. And usually that's on a much smaller scale than a GMC, but in reality, these GMCs are porous, they're all surfaces, and it's not surprising that different conditions in the galaxy will give different chemistries. So basically, the chemistry is very tightly related to the galactic structure. Where the cloud is found in the galaxy will determine its chemistry. And in the case of methanol and HNCO, they are seen along these arms in the outer part. And C2H, for example, is found in the very nucleus within that inner ring. Now, C2H is known to be favored in circumstances where you have high radiation fields. You get a lot of C+, you get a rich gas phase chemistry. What's interesting is, in this case, there is star formation in this galaxy, but it's not where the C2H is. The C2H instead is tracing that nuclear cluster, which is B stars. They're older stars. So it's not hydrogen ionizing radiation that's producing this. Okay, MAPHI2, I will show you the same thing from a MAPHI2. It is similar, pretty similar to IC342. There are slight differences. It's more barred. You can see that here. It's inclined also. It's not face-on. That's part of it. So you see it has a very pronounced bar-like structure in the nucleus. It also has what I'd call a starburst. IC342 has star formation, but this is forming superstar clusters, very luminous starburst in the northern region. So those are the two main differences. And if you look at the chemistry here, these are maps of MAPHI2 made with BIMA. HNC, HC3N, N2H+, C2H, C34S, HNCO, and methanol, and you see that there are extreme differences here also. And there are differences with IC342. We don't have enough galaxies to completely understand this. We do see C2H. It is much more extensive than in IC342, probably due to the starburst. HC3N is a dense gas tracer, and it's found up in the north around the starburst and in the nucleus. So there are certain things we understand. HNCO and methanol are very well correlated, and we have found that in both galaxies. So we did a principal component analysis. We also did this for IC342, but I'm just going to show you the newer result, which is MAPHI2. So this is just looking at the statistics. What do the statistics tell you about the correlations? And so we plot, and I'm saying correlations between the molecules, I mean correlations of their intensities, okay, the intensities of the lines. But actually, for this set of molecules, excitation is not going to explain those differences. They're all in cold gas. They're all sort of moderate density tracers. It's not excitation that produces these differences. So the first principal component, which is the strongest correlation that you find, is that molecules are found in molecular clouds, and this is plotted. The projections of the different molecules, their intensities are along this axis. So basically, 13CO and N2H plus are very good tracers of the overall gas distribution. And we found that in both IC342 and MFI2. Those are good overall gas tracers. C2H, as it turns out, is a good tracer here in MFI2. It's not so good in IC342. Okay, so molecules are found in molecular clouds, so that's nice. It falls out of the statistics. The second principal axis is once you have solved for the first principal axis, then you go orthogonal, you find the next biggest dispersion, and that's going to be your second principal axis. And here we actually have a negative and a positive. There are two groups of molecules that are anti-correlated, and those would be the molecules, well, HNCO, SiO, and methanol are found, let's see, this is the positive here. And on the other hand, on the other side, there's C34S over here, and HC3N, which is found associated with the starburst. So this shows the very good correlation between methanol and HNCO that we found before. And I think before we did the work on IC342, I think the chemistry of methanol, of HNCO was a bit of a question mark. But we see an excellent correlation with methanol, which is known to be formed on grains. And so if the excellent correlation is any indication, then HNCO forms in the same way. So this shows that there are particular chemistries that arise in particular galactic environments, and that the chemistry is closely tied to galactic structure. Okay, now this is something you should never show in a talk. So it's a correlation matrix. So this is individual molecules, 2 by 2, how they correlate. I just want to draw your attention to the highest numbers in here. These are correlation coefficients of 0.94 and 0.90, which are quite high. And that's for the correlation. The highest is HNC with 3 millimeter continuum. 3 millimeter continuum is free emission from ionized gas. And it's also believed to be correlated with infrared emission. And I was just talking with John Black. This is a well-known correlation that was discovered by Gao and Solomon in 2004. For single-dish studies of galaxies, they found that the luminosity in the HCN line was very tightly correlated with the luminosity in infrared, which suggests, and their interpretation was that HCN, which is the dense component of gas in galaxies, is very tightly correlated with star formation, as represented by the infrared luminosity. Now, here we see this holding not on kiloparsec size scales, but down to tens of parsec size scales. Excellent correlation, both galaxies, very strong correlation. And I was talking with John, there is the 14 micron. I know HCN better than HNC. John says HNC does the same thing, only better. That mid-infrared pumping might be a possible explanation for this. At any rate, it's a very interesting correlation, not only perhaps for the chemist, but also for the astrophysicist who might want to do kinematics in a distant galaxy on star-forming gas. If there's an excellent correlation between the star-forming gas and the HNC emission, then you can use the exquisite velocity resolution that we get with heterodyne detectors in the millimeter to do the kinematics of the gas. It's so difficult to do in the infrared or optical. So that's a potentially very useful tracer of star-forming gas. Okay, there are other correlations too. that are interesting, but those were the ones I wanted to point out the strongest. So just sort of in summary on both of these galaxies, here's Phi 2 and IC 342, and you could sort of group into three categories the chemistries that we saw: C2H, which is tracing the star-forming gas, although not always the hydrogen ionizing gas. So sometimes it's kind of the slightly older population of stars, still probably related to C+. And it's very extensive in Phi 2, less so in IC 342. And 2H plus is a good all-over gas tracer, as we're finding, and that's not surprising. What's surprising to me is how bright it is, how easy it is to see in galaxies. And then methanol and HNCO seem to trace along the spiral arms the quiescent gas, which is not forming stars. And whether they are formed by molecules coming off grains in shocks, because they're grain chemistry molecules, believed to be, or whether it's mild star formation warming in the gas is kind of unclear, but we'll have to study that more. Okay, in M82, I'm not going to discuss this too much. We have maps. It's very different. M82 has been described before as a pure starburst galaxy, and we were unable to detect HNCO or methanol here, which is consistent with what we saw before. It has been detected with the 30 meter, but it's weak. Very weak compared to C2H. So in fact, C2H is a very strong molecule in starbursts. It's easily detectable. It might be even more useful than CO, and I think it'll be very common for people to study starbursts with C2H. Okay, so I can sort of summarize what we've found so far. Thinking the gas tracers, such as CO and 2H plus and HNC, kind of. We'll have to watch that one. Spiral arm molecules, which we've seen in quiescent spiral arms, HNCO and methanol. High radiation field molecules, tracing high radiation environments, and perhaps H2 region molecules that may be good tracers of where there are H2 regions. So I think this is what Evina described as mutual stimulation of astrochemistry and astrophysics. This principal component analysis and the spatial correlations between these molecules has been really useful. Just throwing it into the principal component analysis and seeing what correlations tell you about the chemistry has been useful. And in the case, it's shown us that HNCO and methanol are found exactly the same places in these galaxies, very tightly correlated in where they're found within the galaxy. And the variation of chemistry can inform us about galactic structure, for example, using potentially HCN or HNC as a tracer of kinematics of gas. It may be very useful in the future when ALMA comes along. You want to study distant starbursts. You want to know what the rotation curve is of this galaxy at Z of 6. You could perhaps do it with HNC. So the future is ALMA, and I've been waiting for ALMA for a very long time. I remember being a postdoc in one of the early committees on ALMA and saying kind of quietly, I think it should be sub-millimeter. And at the time, it was a millimeter project. So I'm glad to see it's sub-millimeter. And I think there are going to be all sorts of great things we can do, including NGC 253. This was done in 8 hours with IRAM. You can get this in half an hour with ALMA. And then ARP 220 will be visible out to very high redshift. And so systems of this sort that are massively forming stars, which is much more common in the early universe, will have access to. And so chemistry will be very richly rewarding for learning about the evolution of the universe. So I would like to thank Alex very much for helping to train a radio astronomer. Thank you.
Okay. Any questions? Bill.
Is it possible to observe the ion protate HCN brought up the precursor of HMC. See if that's our relationship.
I couldn't answer you offhand, and John.
I think the answer is it's going to be extremely because it has a rather small dipole.
Yeah, that'll affect the interpretation. I mean, you know, ALMA can do amazing things.
Anybody else?
Actually, before I go, I'd like to say one thing I forgot to say, which is nobody mentioned. Until about 5 years ago, I sat on, for a while, on the American Astronomical Society's publication board, and nobody has mentioned, among all the different things that Alex has done, is that he was the editor of the APJ letters for many years, which, with all of those papers, and it's being on the pub board, you learn just how hard it is to be an editor, and it takes really rather amazing people skills, which you don't normally think about but it's really an important part of a successful scientist. So that's a remarkable achievement, and I saw it at firsthand. I saw sort of the back scenes of the publication board, and it's really something. So we appreciate your service there too. How many years was that? Editor. 29? There you go. The Warren Buffett of astrophysics.